Hello everyone and welcome to another episode of the Func Prog podcast. My name is Christopher and today I'm talking with Lachezar Yankov. Lachezar is a Scala developer. He's been working with Scala for the past 5 years and is a big believer in statically type programming languages and having the compiler do work for the programmer instead of the other way around. Yes, so welcome to the podcast, Lachezar. First of all, I know you're a big fan of Scala. That much
Indeed.
I've understood.
That's absolutely right.
Yes. And I heard a talk you had a few months ago now, where you talked about like using Zio and Scala for writing production software. So I was thinking maybe we could talk a little bit about that today.
Sure, I would love to.
Yes.
It was back in October, I believe, for the Scala Stockholm meetup.
Exactly.
And we have had few talks about Zio before that. So I tried to have another one. So that
okay, so this was a different spin on that.
Repetition helps people learn, I guess.
Yeah. What do you say? Like repetition is the mother of learning.
Yes, maybe, and
like that.
The father of something, of boredom or something like that. But so I tried to talk about pragmatic points because functional programming, it's a lot of theory in it. This is why you have so many courses because there is a lot of theory to be taught, and also there is a lot to be learned. So it also makes it interesting for people that enjoy learning. But if you don't necessarily see yourself in that set of people, then you want to focus on pragmatic things, and then Zio is a good, I wouldn't say it's a framework or a library, but ecosystem for writing systems for Scala, for the Scala language.
Yeah, I mean, it's really true what you said, that thing about like people have I don't know. Do you know why is that? I don't think I've ever really reflected properly on like why functional programming or why functional programmers like they seem to love theory a lot. Like I mean, there are like the it feels like, you know, the to-do app tutorial of the functional programming world is like the monad tutorial. Sort of.
Maybe.
Every time you have it like a JavaScript framework, everyone wants to write like, you know, a to-do tutorial for like their favorite JavaScript framework. It feels like every Haskell programmer wants to write their own monad tutorial.
It has to do something with the creators. Like Haskell comes from collaboration between few universities. I mean, the Glasgow Haskell compiler. You know, there should be something about. Also, I believe it was it Lund University, or maybe it was Chalmers. Yeah, in Gothenburg. So
yeah, Chalmers. That's where Agda is from.
But I think one of the founding fathers of Haskell, or the person who decided on the name, is also from there. So
yeah, probably.
It has many contributors or like founding fathers that were essentially professors in different universities. So then, of course, there will be PhD students working on the language and the compiler.
PhD students need something to do.
Of course. And this means that there will be papers, theses, and this means that there are things that people can read and learn about. And the same goes for Scala. Scala is created by Martin Odersky. It's maybe 25 years old now. Don't remember, it was 2001 that was released initially. Martin Odersky is a professor at EPFL. I think it was a Swiss university. He has originally worked on the Java generics. He figured out that it's impossible to introduce hard-coded types or like generics that have generics in Java, and so he created Scala maybe or maybe there was one more iteration before
there was
Scala
something
was
called
invented.
pizza, I think, before Scala, right?
Yeah, I didn't want to say that because if I'm wrong, everyone will make fun of me because pizza is such an interesting name for a language.
Yeah. But now they can make fun of me instead. Like, oh, who's this crazy guy who thought pizza comes before Scala?
I think the funny part would be if I say pasta, then people will like, no, it's pizza, not pasta.
Yeah, but he's working on this thing called caprese now, so it's like
Yes.
there it feels like there's some kind of like maybe there's some food theme here, at least for like prototype.
But there will be again PhD students or like people in the academia working on it, which means that there will be things written on paper that somebody else can read about, or like ideas that could be developed in those compilers. So from that point of view, those languages will forever be languages that will adopt ideas that are a bit different, or maybe a bit not necessarily as pragmatic as the ordinary engineering languages that companies essentially push through, and this is maybe what it makes them interesting, in my opinion.
It feels like Scala was designed from the beginning to be a pragmatic language, right? I mean, or I guess I suppose the name Scala is supposed to be short form for like scalable language.
Yeah. True. It is pragmatic. It has a lot, however. So you could start simple. There are projects that don't use effect systems or are very straightforward to use. You can still, throw exceptions and print without effect system. But at the same time, you can do this fully functional, effectful type of programming, which is what attracts everyone, I believe, because nobody really picks Scala to do just Java style of programming, because you have this duality of paradigms. Scala supports object orientation, but also supports pure functional programming. It has a null in Scala 2 and Scala 3. I think now it's maybe a union type of whatever your type is, and null. So there are some changes there. But to be fully compatible with Java, it needs to be able to do the exact same, or to have the exact same weak sides as Java has.
Yeah. But you said something interesting there, I think. Like, what is an effect system for the audience?
Great question. I don't know the formal definition, to be honest, but for me, an effect system, in a pure theoretical sense, you want your program to be referentially transparent, so you would wrap your computations inside of a type like IO, and then you have a runtime that runs those computations. And I don't even think that anyone listening, like if you haven't worked with the effect system, you're probably not going to understand anything. But from a practical point of view, you can think of an effect system as a way to distinguish between pure computations, meaning that you have a function that takes a value and outputs a value, and everything else. And everything else could be printing to the standard IO, print or doing some kind of a database request or network request. And the thing about the first type of computations, where you have this kind of a pure function or pure computation, is that it's very much always predictable, and it could be replaced by just maybe the same value, or like not necessarily the same value, but some kind of map between your input and output. Whereas everything else that involves writing to the console or reading from a database is in an essence a thing that you cannot replace with this kind of map, because it needs to have its imprint on the world. So you cannot really, you can take one pure expression, assign it to a value, and then reuse this value multiple times. You cannot do that if your function writes to the database, because when you execute this function twice, you would want to see the result in the database twice. Whereas if you execute the function that takes a value and outputs a number, then you can just assign the result and then reuse it as many times if you want. And effect systems helps you model those effectful computations as pure values and then chain them together and run them. I'm already confused by my explanation.
Yeah, but I think it's like, no, I think it's a good explanation, and I think to your point about like it kind of has to do with like purity, and I guess maybe it's easier to define like what an effect is. And I mean, basically, effect is anything that's, like you said, that's non-deterministic. Like you can't just express it in terms of like pure functions that that you sort of apply to each other. I mean, it's, yeah, like you said, stuff like IO, for example, randomness. I mean, some would also say that throwing an exception is also an effect, because that sort of makes the program jump from one place in the code to another, and that's not like, I mean, that's not really a function that does that. That's something else.
Yes, exactly. In a way, those effect systems let you model all these things, all the dirty things that changes the world in a uniform way, so that you can have control over them, or like good observability over them. It comes at a cost, so you will have a nicer mental model to work with them. You might have more allocations. So every time you have IO, that's an allocation on the heap for your computation to happen in Scala, at least. Haskell, I think it's lazy language, so I'd expect that this is not necessarily the case. But also, I think it's a bit harder to manage larger programs in Haskell, because then suddenly you might have a lot of things that are being evaluated in the worst possible time in your program, and lose track of, or like have a spike in memory consumption and things like that.
Yeah, laziness is kind of like that's a it's a bit of a different beast, I guess. Sometimes hard to reason about. But what was I going to say? So is Zio an effect system?
It is. It is an effect system. It is a bit special because it is a practical effect system.
Okay, does that make it unique in the world?
Probably, but my journey with Zio essentially started with Haskell. So before I even knew about Zio, and it started with reader TIO. So Rio Monad. There is like an ecosystem developed from FP Complete, Michael Neumann, which in a sense boils down to reader T, IO. Reader T is a monotransform between reader and your effect, and IO is the effect type in Haskell. And for people that don't know Haskell, you essentially if you want to print to the console, you will need to be in the IO monad. If you want to have some kind of environment and print to the console, then you would need to switch between the reader monad, which keeps your environment, and IO. So you have reader TIO. And I worked with this for a while. You have a stack of monads, so this kind of a vertical stack of things that you need to go through in order to perform a particular effect. For example, maybe you have a logger and then you have to lift to it, or like to transform to that monad so that you can log.
Okay, so
after that,
yeah.
I was saying that after I worked a bit with it and struggled a bit with it, essentially, I emerged as a really versed junior Haskell developer, I would say, for about 9 months. But then I started working with Zio, and I don't even know how it happened. It was just by sheer incident. And then I didn't know anything. I didn't know Scala, I didn't know Zio or anything like that. I was like, this thing reminds me of Rio. And then I looked more into it, and the more I look, the more I see similarities. Until maybe 6 months in, I actually watched a presentation from John DeGo, who is the creator of Zio, giving credits to Michael Neumann and to Reader T, to Rio Monad, essentially, and that approach.
So
which was very, very
you were right
eye-opening
in your instinct, like you spotted you weren't wrong.
No, but the approach with Zio, the pragmatism comes for the fact that you don't have this stack of monad transformers, and you have everything in a single monad, which is the Zio type, which has 3 type parameters: one for the environment, one for the failures or the errors that you want to signal, and the last one is for the result of your computation.
So
which if I just can finish, which just squashes together reader, either, and your effect in a single thing, so that you don't need to go back and forth between them. It probably saves on computation. The price that we pay most likely is that you need to learn maybe 200 functions.
Okay.
You don't need 200 of them to be productive. Maybe you need 12 or 20. But because you have this Cartesian product, you don't have this going back and forth with the monads, and each monad have maybe 20 or something, and they share names and things like that. Instead of that, you have a specific function that acts on the error, or specific function that acts on the environment, specific function that will act on something else, which is a small price to pay, because there are ways to be to learn this and to be efficient with it. But your application, then it will have less work to do, because you will not jump through monads.
Okay, so just so that I let me see if I understood it correctly. So, I mean, you were talking about like monad stacks before, and as far as I understand, like, I mean, one way you can do effect systems is like when you have a particular type of effect in your function, you return an instance of that monad. So, for example, let's say a really simple example would be if you want to simulate exceptions in Haskell, for example, you can use the either type, which gives you like two, like either like successful or failure value. And then you want to sort of bring I/O into this thing. You want to write to the hard. You want to like persist something to disk or something like that. But the problem is that, like, you can't just compose these two, so you sort of need to transform them somehow. And in the Rio monad, do you sort of and just for the listeners, the way you usually do this is that you can sort of lift them into like a common monad. So Haskell, for example, ships with a bunch of stuff like this. For example, you have the what's it called? Like there are monad transformer libraries that lets you sort of create like an either I/O monad, and in Haskell this works. I mean, by the fact that it has like higher kind of types, so you can reason about like monads as a generic class of types, which makes monad transformers like
but if you do the transformations, you still need to go back and forth, I guess, by hand, or like have some kind of a type class that does this automatical lifting and unlifting to the correct monad. And I don't remember all that much because it was a long time ago. But I remember that we've made, like, the project was made in a way that is ergonomic, and it was not necessarily very hard to work with, but it was a bit hard to understand the stack, or like to know what's going on. Whereas in Zio, it's quite easy to explain that you have these built-in things, and then there are functions that will let you query or like extract something from the environment, and there will be functions that will let you signal a failure. So all this kind of theory, in a way, goes away. So you don't need to think about it.
But the way Zio handles it is that you only have a Zio monad, right?
Yes.
And then that gets composed, or rather, maybe you can tell me, like, okay, how do you compose if you have one function that returns one Zio monad and you have another function that returns another Zio monad? Like how do they compose? Like how do you sort of smash them together?
Yeah, well, the pragmatic answer is you monads don't compose unless you use it nicely. But you flat map, so you would have essentially you call bind, and then you return, because you have the same monad, so you always return that monad. But yeah, so it is. It becomes like a DSL where you, for example, to query the environment and to get a dependency, you use service. To signal a failure, you use fail, like Zio fail. To return a successful type, you use Zio succeed. And all this will be in a for comprehension, which is like a glorified chain of flat maps with a map at the end.
Yeah, it's like the Scala flavor of like do notation.
Yes,
I'm not a Scala programmer, so.
But I had listened to your first episode before everybody else, and I really enjoyed the conversation. And one of the things that the guest mentioned is like what makes successful strongly type safe functional language is the presence of a do block or a for comprehension or something that can give you ergonomics to chain these computations.
Yeah, I actually have recorded a presentation about this at an F# meetup just recently, and it's sort of like, if you don't have this, especially when you have like, let's say you're trying to chain, like you have multiple either monads or something like that, and you sort of want to use multiple values in parallel to, for example, build like a user record or something like that, without like some way of like unwrapping these monads, the code becomes really ugly, because you have to, like, the problem is that every time you want to introduce a new variable, you have to do that through like a lambda function, basically. And then like, it's very easy to end up with this, like, deeply nested. I mean, you're basically back to like callback hell, right? Like the classic like callback hell from JavaScript, where if you want to use like a I mean, if you're just like threading values through multiple binds or flat maps, I mean, that's not so bad. The problem comes when you need to, like, oh, I want to take these like 3 results or something like that. I want to combine them into like a single thing. Yeah, that can become kind of nasty. But yes, like you said, it's really good to have some kind of like do notation or.
Yeah, it gives you the ergonomics. Yeah, so essentially Zio, I worked with it maybe for 3 years, and it was an eye-opening experience because programming stopped being, I didn't, or to say it better, I stopped having to remember everything about the context in my head. It was more of a what is called one of these really championship stages where you have multiple checkpoints to go through. And you don't necessarily even need to start from the start and go to the finish. You can start from the finish, do a bit of work, then continue from the start. And then somewhere in the middle, you'll meet each other. You'll meet the start with the finish. So it became like this kind of a checkpoint workflow where you pick your types, you try to express constraints through types, and you know that you have the ability to signal errors, your domain errors, with the failure type in Zio, and you know that you have the ability to have dependencies part of your monad, and you can pull them and use them. And you can build complex systems, like domain-heavy systems with this, because each of, like your environment essentially will carry services that represents your domain, like maybe a user service or a audit service or authentication service. Then your domain could be, or the errors that you might have in your domain, they could be mixed together when you use Scala 3 actually. Scala 2 doesn't have untagged union type, so you have to do some kind of a common Zio trait. So a Zio trait that is common for all your errors. But if you use Scala 3, then you have this ad hoc untagged union types where you have a user error maybe and then audit error. They don't share any kind of a parent. So and you can like a lot of things fit or like come into places using this, because then you can decompose complicated things into smaller services. Those services emit some errors. You can decide where to handle those errors. The compiler will be your quote-unquote copilot, not to be mistaken with GitHub Copilot. But the compiler will be a buddy to you that will stay next to you and remind you. So you have these and these errors here. What do we do? Do we propagate them onwards? Do we handle them? We need to make a decision. What would it be? Oftentimes you make your domain errors somewhat presentable, or like if they affect the client, most likely they will leak to the client layer, or like because sometimes you want to show an error to the user, for example. Other times you'll swallow them, promote them to a fatal errors. So in Zio you have defects, failures, and I think it's called I don't know if it was called PANI, but essentially out of memory. So errors that really end your application.
Yeah, it's like really nothing you can do here.
Yeah, the failures are your domain errors. So things that you want to communicate because your domain already communicates them. Like before you automate or build the system, you have some kind of manual process, and this manual process you have some kind of problems or issues that are part of this, and they will transition into being domain errors when you start building the system. And then everything else are things that you cannot recover from. So if you don't have disk space, if your database connection is down, you cannot do anything about. But if your username is already taken, well, that's a domain error.
Yeah.
You have the term user, and it has some properties, and it has some things that couldn't be duplicated. Maybe in distant future, you have, instead of username, you have an email that needs to be unique. So your username could now be reused among different instances or different people. And in this case, you change your domain to reflect this, and you no longer have this kind of a username needs to be unique constraint.
Yeah, can we talk a bit about like I think what it's called, what the Zio calls channels, or because the Zio monad, and correct me if I'm wrong here, Lachezar, but the Zio monad is like parameterized on 3 types, and
yeah,
are they called channels, or what is the? Am I using
no, maybe you mean the
terminology?
error channel. So the
Okay,
Zio
so it's just one
monad
error channel.
or
Yeah.
the Zio type has 3 type parameters, which is environment, error, and the result of your computation. And the environment holds, it could hold actually anything, but it will be your domain-specific services, like in sense of dependency injections, or like dependencies of your application. So when you model a business application, maybe you have a user service, and then maybe you have an item service, and then you will use them to decompose the complex system into smaller services that could be mocked if you want to unit test, that could be easily reasoned. And then the error channel will be the failures, or like the domain errors of your system. You have also defects, which are unrecoverable errors. So this is like a different error channel, I guess. And then the last one is, I need to look it up. Okay, fatal errors.
Okay, so that's a separate.
This is the last one. But the last one, it's things that you cannot do anything about, like out of memory and virtual machine error, Stack Overflow error.
Yeah, I mean that.
But whereas the first 2, you can do things. You can go from a domain-specific error into unrecoverable error, and from unrecoverable error, you can go into domain-specific error as well. And the idea is like your failures. If you like take a concrete example, if you build a REST API or some kind of web API, you have your 400s and your 500s. Most likely, your 400s will be these domain-specific errors, but not only. And then your unrecoverable errors, they will be 500 always, because you cannot recover from them. Whereas, when you have a domain-specific error that says the username is already taken, you want to communicate this to the user. So you have 400 and something, or maybe just 400, with an error message, username already taken.
Yeah, exactly. So you have like the recoverable errors where you want to give some kind of like maybe some user feedback, and then you have those like the things you really can't do anything about, like out of disk space is a good one. I mean, but what I found really cool when I saw your presentation was the fact that you can, like you said before as well, that you can leverage these untagged unions in Scala to sort of combine error sources. Because that's a common like bugbear when you like both in effect systems and otherwise in other functional programming languages, because usually you have these sum types which are really nice because they let you model like a bunch of different types as a single type, but the problem is that the sum type always has this like tree structure. But with the Scala union types, you can sort of like, and how does you can sort of like merge two types together, right?
Yeah. So it is a Scala tree actually featured.
Yeah, Scala 2
In
didn't.
Scala 2, Scala 2 was not having this, but Scala 3 has union types and also intersection types. So you can do this ad hoc, how to say it, ad hoc, it's either this type or that type kind of thing. And the power of this is like if you have an effect that comes, from your item service, maybe, the product is depleted or the product is out of stock. And then your user service might have the user is suspended or something like that. So if you have an effect that checks the product or wants to purchase a particular product, and also an effect that wants to pay to the business that you're purchasing from. This function that does these two things will have a result error that is, the item is depleted, it's out of stock. And also another possible error is that business is no longer active or suspended. So you have to model these two, or you model these two things in separation. But when you try to combine and create a more complex workflow, all these errors will be automatically added to the result type of your computation. But this was really bad example. Let's think of a better one.
But I mean, I think the general problem is like, I mean, you have the same thing. Like even if you just go down to just using regular, like some kind of result or like either type, for example, like usually you have, I mean, different operations usually have completely different errors. And the results are usually like the successful results are, okay, because you're only interested in one of, like, operating on one of them at a time, and usually you sort of pipe them together. So that, like, you might go, for example, let's say I successfully managed to construct a user, then I might take that user and I might, I don't know, construct like a blog post record or something like that. And that might also fail, and that's no problem, because, like, then it's just a mapping from user to a blog post with maybe some extra inputs on the side. The problem is that the user has a set of errors that is specific to the user. For example, like maybe the username was invalid, maybe the email was invalid or something like that. And then the blog post has a separate set of errors, like maybe the title cannot be empty, maybe the post body cannot be empty, something like that. Maybe you cannot make the publication date in the past or something like that. And the thing is, like, you want to combine these two errors into like a common, like, literally a union of all of them. But the problem when you only have like some types, like these tagged unions, is that you can't just take these two types and combine them and say, like, well, I know I have a third type, because then you explicitly need to create this third type by hand, or, like, I guess in like you said in Scala, you have to have some kind of like common trait. Is that like sort of like a Scala type class interface thing, I guess?
Yes, so you have to, all your domain errors, if you have hundreds or 50 or some big number of services with their specific errors, they all need to share the same super class, or like something. In Scala 2, you need to make them descendant of one common thing. which is your error, because then you'll be able to use the common thing in your handler as at the edge, essentially, where you have your API definition. But in Scala 3, you don't need to do that. You would have this union type of your user errors and your item errors, or your block errors. I forgot the article errors and the user error, maybe it was your example. And then the compiler will make sure to tell you what you need to handle. So you have this kind of a way to decompose a problem, to build essentially different parts of it. And then once you start integrating those parts, you have this nice byproduct or feature of the compiler that will tell you need to handle this and these cases now. Which is in a way very similar to these exhaustive checks, or like the ability for the compiler to require you to match all possible cases, or to handle all possible cases in a sealed trait, for example. So it feels exactly the same. It works, however, in a more ad hoc manner. And other languages might not have this. Many languages nowadays have this. They can do exhaustive matches, but other languages don't have it. And when you don't have it, then you need to keep all this knowledge, all this context in your head, and be careful to not miss a case.
Yeah, that historically that has worked out great.
Yeah.
Like, yeah, just don't make any mistakes. Has been a historically not a very successful strategy.
And when you think about it, you want to have to spend time on the actual problem that you're solving, not on remembering things. And Scala is very good at this, and Haskell and other languages, because you can write code for a few days, and then run it, and it's very likely that it will start, and it might not produce what you want, but there won't be any runtime errors because of this exhaustive pattern matching and exhaustive checks. Which is really amazing feel, because you can write for a few days and then run it, and then suddenly everything works. Or maybe you forget to add configuration and then your application dies, but after you add the configuration, then everything works. And it's this Haskell phrase that if it compiles, then it works. That really inspired me or captivated me. It's not, it is true in a sense, but also it is not true, because if it compiles, it will probably start, but it will do something wrong. So,
yeah.
but in a way, at least it will start, and you will not have some kind of a strange runtime error because you forgot to fulfill some kind of weird requirement of some library that you're using.
Yeah. No, I agree. But just for fun, let me play devil's advocate for a second here. Like, couldn't you say the exact same thing about object-oriented programming?
Which one thing?
The fact that if it compiles, it works. Like, how come this has sort of become sort of the trademark of the Haskell and Scala and other like ML type languages?
I don't think it necessarily has to do something with whether it's object oriented or not. It has to do with the ability to do more things during compilation, or do more checks during compilation, which object oriented languages have not been able to do. But I also hear many people nowadays promoting or like going away from the idea that you want to do inheritance in object-oriented languages, or do the things that object-oriented languages are great at. And those people are like one step away from just switching to functional programming, because we don't really, like, functional programming has such a bad name because it's not about the functions. I mean, obviously, I'm not going to tell you that, like, it's about, type safety. It's about the compiler doing work for you. And I don't care if you're going to write one function with 1,000,000 lines. You should probably not do that. Or you're going to have, multiple functions that call each other, interact with each other. All you care about is to have programs that work. And when you don't have necessarily the compiler able to check for you that your program seems it's going to not fail when you start it, you need to write a lot of unit tests to prove that, right? Because this is what you do. If the compiler cannot prove to you that your thing will run, you write a test that runs your thing and checks that it doesn't crash. If the compiler can prove that, then you don't need to write the unit test. Then you focus on unit tests that test that your computation, your function does the right thing. It outputs 42 when you want it to output 42.
Yeah.
Not that it throws a runtime exception for the case when you input 0 to it, for example. And then object-oriented languages, they historically have been very much pro mutations and pro state, mutable state, whereas functional languages have been kind of reluctant to this, and it probably doesn't work very well. It would not work in Haskell. Haskell will tell you that this is, needs to happen in the I/O because you're changing the world. If you have a shared mutable state, and if you think about it, it does that. So you have tools to work without it on it using ref, for example. And it's very much similar for Scala. You'd have the option to use mutable shared state and use object orientation, but this will come with issues for you. So you would have other primitives that are concurrently safe, that will prevent you from having. It will prevent you from having this shared state being modified at the same time and having race conditions with it. And maybe I should actually also mention, like, the effect system itself, it could, I think all of them, or at least the ones that I have worked, they have structured concurrency. So you can spawn fibers or green threads that work independently to each other. And they, of course, can interact with the environment or with this shared mutable state, but the shared mutable state is designed in a special way that you cannot have race conditions, or you cannot have two fibers overriding each other, because the way that writing happens is there will be something that will make sure that it becomes in sequence, which in Haskell, and I think in Zio and Katz effect, the ref type does by using compare and swap algorithm. So you have some kind of guarantees that even if you have some shared mutable state, it is referentially transparent, meaning that only when you try to run update on it, it will actually be, when you try to run update on it, it will actually be done in a way that you don't overwrite values in unpredictable way.
So it's kind of like a, how can I say, like quantum superposition of mutability. It's like if the only collapses, like to the observer, it seems immutable, but like,
yeah, it is, what is it, compare and swap. So if when you try to update something, the value will be checked before you start and at the moment you want to update. And if the value has changed, then you'll be put again in the queue, and you wait your turn.
Mm.
In a way, you prevent this kind of overwrites to happen because you synchronize the writing without doing actual synchronization. Because so some of the failed writes will go back into the queue, will wait for their line to happen, but others will be able to go through.
Is this what like software transactional memory is about? I always forget what's
Oh no, I think it's so software transactional memory. I think it's essentially lets you have data structures that needs to be updated in particular way, so that you don't have. Because if you have a map, for example, and you only act on one entry of the map, you don't need to lock all other entries.
No, that's true. Like if you view it as a
Or
tree, you only need to lock like the subtree, for example.
yes, but honestly, I have never used it.
No, I mean it's a like staple of like concurrent programming in Haskell, and I've never. I don't know. I shouldn't talk about it since I've never used it either.
No,
Yes.
I think the reality of the systems that I have worked with is that they transform data and write them to a database and back and forth. So you would have very little shared state. You have a lot of transformations coming through your application and going into a database or to some other service. And in this actually makes everything much simpler because you don't need to even care about what happens if your application needs to restart, because you never restart the database, right?
No.
But your application obviously needs to be updated.
You hope and pray that you will not have to. I guess that's the that's the thing. And yeah, I mean for a lot of this, like I mean the way we structure most applications today is like you have these application servers that are stateless, and I mean that goes very well, I think, with the whole functional paradigm, because I mean one thing that does become like a bit awkward in functional programming is when you actually do need mutation for like very high speed computation, etc. And I know that the OCaml developers are sort of working on, because Jane Street, they do like a lot of trading algorithms, or like, they really need performances. Then you need, you want efficient mutation capabilities, but for us mortals, like you and me, working on CRUD apps every day, like we don't really need to care so much about that. It's like usually we can get away with just transforming.
Yeah, and Zio is really great at building CRUD apps, and not only CRUD apps, but because you have this kind of domain, or like maybe using domain-driven design, you have your database tables modeled as repositories and things like that. So you have many tables, you have many repositories in your environment, and you have some kind of a common interface to interact with them, and then you have the implementation, and the implementation would care actually for the SQL and what kind of SQL you write. And then you have this kind of separation. You have interfaces or traits. They're called traits. I might occasionally say interface, but what I mean is that it's a contract that you work with. You have the implementation in separation, so you can decide whether it's going to be using a database or something else. And then your services interact with this contract or with this interface. They don't care about the actual implementation. And this is quite inefficient in a sense that you have layers of separation. I don't think you'll achieve huge performance out of this, but you need to ask yourself: do I build something that truly needs high performance? And if you truly need high performance, maybe you need to pick tools that will accomplish this. And if, however, you want correctness and decent performance, then Zio is a good tool to be used, because you'll be able to model your complex business domain and your complex business processes in a easy to understand manner, or at least manageable manner. And you will accomplish this correctness and good performance as a result of this. So everything, it depends what you want to do.
Yeah.
But I was about to ask you this.
Yeah.
OCaml have IO monad?
No, they like OCaml is not a pure language, so they can just do like, well, I mean, it has its roots in ML, so it even has like, built-in support for mutability. Like you can just mutate variables all you want. Like, yes, you heard me, Haskell developers.
So in an essence, you don't have any kind of the same safeguards or guarantees that you would have in a language that has an IO monad, maybe, but you gain performance because you can mutate in place. Like mutating in place is just more performant. There is no way to, like, if I have to do more work to allocate memory and do things instead of doing in place, obviously more work means it takes time, performance goes down, and there is no way around it.
Yeah. And I mean, the interesting thing I think about that is that it's very hard as well to, like, make that as sort of like a blanket statement as well. Because, for example, like, when you talk about like high performance languages, for example, Go, people usually, like, it's usually mentioned in the same breath as like, high performance. Especially for like being a garbage collected language. Like it's sort of like not directly competing with Rust and SIG in my world, because it's like, I mean, yeah, it's sort of apples and pears, right? But the funny thing about like, and Go has mutable variables, which is also like, very efficient. It's basically, garbage reference counted pointers, I think, or maybe not reference counted. Like, I'm not a Go programmer either, so. But anyway, it has garbage collection. But the problem with these kind of things is that like mutability and garbage collection are kind of tricky to get right, or so no mutability is the wrong word too, but mutable pointers or like pointer ownership and all like that kind of thing, because if you compare Go to Erlang, I mean Erlang doesn't have any kind of mutability at all. Instead, what you have is like you have processes that can send messages to each other, and this is like, and you can sort of emulate mutability by sending a message to a process, and then that process will have that, like the data from that message in memory. So if you really wanted to, you could model like a mutable variable as a process that you send update messages to. And like I said, this doesn't sound very efficient, but I've seen personally, like, or I've seen Erlang services that have scaled very, very well under load, and then Go services that have been struggling under the same load, because the garbage collection becomes much more difficult. In Erlang, once a process has completed, there's nothing that can like point into that process. So all the memory allocated by that process, you can just reclaim like instantly. It's trivial. But in Go, it's much more difficult. It's like you have to check like, okay, can I deallocate all this memory? Like, is someone else like holding a pointer to this thing over here? So, I mean, it's I think it's, I don't know where I'm going with this even, but I think it's an interesting property that sometimes you have these things that sort of like on the surface, they seem like, okay, yeah, that's the performant way to do it. But then you run into these like cases where like it might not scale because it becomes hard to reason about. And I think this works on like multiple levels, just like you said with how easy it is to reason about code. I mean, when you have all these monads and effect systems and stuff, and it's kind of easy to say like, oh, this is so complex. Why not just do it the simple way with like, just use regular plain effects, or like what we functional programmers like to call direct style.
Yeah, direct style.
Because that's so weird to functional programmers, just do mutating things, so that we have to have a special name for it. But like it might seem much simpler when programming in the small, but when programming in the large, it becomes incredibly complex.
Yeah, and especially if you handle money or anything like that, you cannot afford to have some kind of a dummy runtime error happening in the middle of transaction. And not even just money transaction. It could be a game round transaction on your favorite, slots slots machine that you or slot game that you're playing.
Yeah.
So you need to have some guarantees, and you're ready to trade performance for those guarantees.
Because I think in the presentation you said something that I really liked, like a good brand. It's brands are important, I've understood, and like you said something like you like to use headline-driven development.
Yeah, I think I mentioned that, and I don't know if I invented it or not, or maybe there is a better name, but in an essence, everything boils down to when you write Java or when you write C#, no, I haven't written a single line of C#, you don't know what exceptions will come out, right? You in Java you have checked exceptions that nobody uses, or people say don't use them. And then you need to look, like the skilled Java developers, they will look, what will the underlying method that you invoke, what will throw, and they'll make sure to handle those, or maybe not handle them if they need to bubble up. And if you look at the Haskell program at the same time, you'll see it's a lot of type parameters, and these type parameters have some kind of constraints on them, and you're trying to communicate in the header of your function. What is this function using? What input and what output, or like what are the capabilities of your monads and the inputs and the outputs? And the same thing is true for all effect systems, the Katz effect and Zio including. But the powerful thing of Zio is like you can, with Scala you can have this kind of a union type of your errors and a intersection type of your environment. So what services your effect depends on. In a single line. It might be a very long line, fine. But it's one line that you're going to read. And then you're going to decide based on this one line, do I need to read the implementation of this function? It's very easy to go through these kind of headlines, like you do in a newspaper, and decide, this article is not interesting for me. Oh, this is interesting headline. I'm going to read what it does now. And this helps for you to discover information. Or quickly to discover if something is of interest to you or not. And the same goes for, even if you take pure functions and effectful functions. A pure function, it doesn't have Zio type. It takes an input and an output something. So what I do, I just replace that function with whatever it returns. If it returns an int, I'll just say, oh, this is forever 42. And then I'll keep on reading. And my brain power is focused only on effectful things, only on functions that does kind of a side effect to the world. And then I started liberating, allocations in my brain. My brain is free now to take much more things. But I cannot also go back to the old style of programming, I noticed.
Yeah.
Just remembering what I need to, like, this thing is throwing or this thing is returning a tuple, but sometimes it returns, a single element. It's just, I'm like, the compiler does all this for me. I expect it to do for me. And if I have to do it by hand, I'm back at square one. I'll have runtime exceptions in my applications. But and that's the power of having a compiler that does more than just translation between code, syntax and machine code. You need a compiler that does work for you. So the compiler, like Haskell and Scala, they're tools. They're not just compilers. They're like a set of tools that can produce code for you through macros, that can check things for you. And this is work that you don't need to do. And this is the powerful thing about it. And when you say Erlang and Elixir, I've worked with Elixir. I was very much big fan of it before it was even released as version 1. And I still feel like the Beam virtual machine is great, and it's battle tested. It's maybe 30 years old now or even more. But I can't really write good Elixir code after writing Scala, I feel. Or maybe I don't enjoy it as much because I don't have the same guarantees that I expect Scala to have. And then there are languages built on top of Beam that are type safe now, or have at least statically typed, like Gleam. And they're a huge step in the right direction, but of course I think Gleam has its own OTP, so it will not use the battle tested OTP that comes from Erlang. And I don't know if it is a port. Is it just a port one-to-one from the original OTP? Is it something new? So a lot of like unknowns. That for me personally, I'll see it as a potential, problem if I start using Beam with OTP, because OTP is battle tested, and then suddenly somebody tells me, "Oh, you use some other OTP now, so not the original Beam OTP." And one last thing I want to add is, like, Elixir now has type safety in a sense that, or at least one of the last versions, it has the ability to check that the tuples of your functions, or essentially will communicate to you what possible tuples your function will return. And when I wrote some Elixir recently, and then the VS Code extension for Elixir was telling me those stuff, and I was like, is it some dielixir or some linting tool that's very clever? Oh wow, that's really nice. And then later on, I read that we are adding this thing as a step towards having, I guess, static types and type safety. And I was like, that's really cool. That's really cool, because Elixir has a lot of good things. It has the with statement, which is like do block for either, because you can communicate errors and successes. You have multiple lines. Each one of them matches against something that you expect. If it doesn't match, then you go into your else statement and you get what was the actual result that it didn't match. And then you can tag each line with some kind of a special word or like keyword, and then you know which line actually created the error, and then you can do something about it, which is a very, very long way to describe for comprehension with an either monad in Scala, or do block with an either monad in Haskell. So it has a lot of, it has also, protocols. So you can have something like type classes.
Yeah, like polymorphism.
Extending existing types. I think this is what was doing, at least. So if you squint your eyes, you'll see a lot of similarities. Just the compiler is not there. There is no, it's just translations. and this is what Haskell and Scala do. They have the compiler that does work for you.
Yeah, no, I think that's very interesting. And like, I mean, there's lots of things to unpack here, I think. I mean, one thing is like, there's always, I think there's some kind of like inevitable tension between like dynamic and static typing when it comes to like live systems. Like Lisp systems or Smalltalk or Erlang. It's like, the problem there is like, it's type systems are really like, I mean, they are, if you think about it, it's a statement about the code the way it looks right now. And it's very difficult. It's like a big, like hard challenge, I think, to take that like approach and try to fit that onto a system that's running. Like you add time to the equation. Because like the type system only tells you like, okay, is this like, does this make sense logically at this point in time? But then it's like, okay, if I want to upgrade a piece of the code, like how should the type system reason about that? And it's kind of interesting, like, for example, in Erlang you have records, but under the hood they are just like tuples with like n number of elements that have like, that get annotated by the compiler. And it sort of has to be that way, because like, what if like Erlang systems can be upgraded while they are running? So what if you receive a record in a message like that was in flight when the code upgrade happened, like, that type no longer exists. And I guess this is what they're doing with Unison, which I think is really, really interesting to like try to bridge these worlds. I'm not sure like exactly. I know kind of some parts of their solution. I'm not sure how they're going to handle like, state, for example. But I know the type checker can sort of like like we were talking about, like, transactional, like you can do transactional upgrades of your code base and things like that. But I think there's always going to be this tension, because it's a difficult problem. And I think another thing is like, it sort of depends on what problem you have. Like if you have a really large code base with lots of domain logic, I mean, the type system can really help you, because there is a lot of how can I say, the type systems kind of becomes like your rule book for what you can and can't express in your domain. And when you have a lot of rules, that's very helpful.
Yeah, essentially you make illegal states unrepresentable, which is another way to say you eliminate classes of errors, or you, without having to write unit tests, you prove that something cannot happen. And if it happens, well, it's a compiler bug compiler, or not bug, compiler bug.
Yeah.
And then most likely somebody else already noticed it and it's fixed. Also in stable compilers like or high profile projects like Scala, those things never surface to production, or like they're caught during nightly builds or like during alpha tests.
Yeah, I mean, it's like in a mature compiler you would catch those.
But like I want to just go back to the OP. I don't know if maybe it's possible to have, because Scala supports OP, so maybe it's possible to build equally great system using OP, or like with type safety and exhaustive checks and all. Probably Comly Hoy, I think it's a very famous like direct style kind of projects that are developed by one person essentially working at, I think it was Facebook. But I have not really worked with that, and the reason why I have not is because it's the functional programming part of Scala is so much more popular than the direct style. Maybe because I don't know. Maybe because there is more courses and theory to learn. And then, but maybe another problem is like mixing behavior and state.
Yeah.
Is
But
this the problem?
I just want
Maybe
to say
that's the
that
problem.
if you want to program a direct style Scala, I think they even made like a complete language around that idea. I think it's called Kotlin.
Yeah, I mean, I don't know. Is this the better Java, or is the Scala the better Java, or is the Scala the better Kotlin, or is I lost track of it, honestly.
Sorry,
Um,
you were saying the
yeah, but so object orientation and mutable state. Maybe that's the problem. Maybe this is why domain-driven design using object-oriented languages never really worked for me. Or maybe because I wasn't having enough experience. It's somewhere in between those two. But the fact that I read people mentioning like, oh, you don't do inheritance or like don't do something in when they work with object-oriented language, for me indicates that there is something wrong with that paradigm. Maybe it's hard to reason. Maybe it's hard to on a paper. It is, you know, the car is an object, or like the dog is an object, and a cat is an object, and they're all animals, so they have a super class, or
yeah.
the dog is a class and the cat is a class, and they have a super class or interface called animal. But the moment that you have a mutable state in them, suddenly things start to become hard and not work the way that you expect them to do. And if you don't do inheritance, if you don't do those things that object-oriented paradigm talks about, then maybe you're not doing object orientation at all. Maybe you're just writing functional programming style code.
But I think one of the big problems with OOP is like if you compare like OOP and like we talked about before, sum types and exhaustiveness checks, they are sort of the same thing if you think about it. Like if I declare like and in some cases they are the same. I think in Scala, I don't know what it's like now, but I guess don't they implement like tagged unions with like sealed classes or something like that?
So Scala 2, you have a sealed trait, and you extend it. And sealed essentially means that all its descendants are declared in the same companion object or the same file, and maybe there's some more rules. Yeah, but it is what Haskell does, it is not what Haskell does. So Haskell doesn't have subtyping. So in Scala you have subtyping. So if you want to communicate that the function takes only one child of your sealed trait, you can very easily just say that the function takes your, I don't know, dog instead of animal. But in Haskell, you can do the same if you have an extension like data kinds, I think it was called, or things like that, even though you don't have subtyping. So the reason is sometimes when you write code, you just want to have a function that only takes a dog, not an animal.
Yeah.
And people find a way. People find a way because this is useful, pragmatic thing to have. So I wouldn't say I'm a professor at Scala or Haskell, but I would say I enjoyed a pragmatic thing, and this is why I enjoyed Zio, because it was a bit of a framework with those with 3 type parameters, with the domain services and with essentially your environment and your error types, domain errors, and your result type. And I understand that the flat map thing is a bit esoteric at first when you see it, but also there is enough information on the internet why it exists and how you can work around it. The good thing at the end is you sit down and write. I mean, at first you struggle, of course, with the new language, but eventually once you become decent at the language and you'll be able to produce a system after 3 days of writing that runs. Like you just compile it and then you run it and it runs. And this is something that I cannot say, like, even if you're a very good Java developer and you know everything and you write for 3 days, at the end of day number 3, I think your system will boot up and you have runtime exception, like maybe 5 minutes after you start, testing your API or whatever you have developed. And this is all because, I mean, maybe no pointer exception, or maybe because you forgot particular case. You forget particular cases because you're just a person. You don't have some superpowers. Your brain is, it might be tired, or you might just think about something else, or you have missed the one case.
Yeah.
And when it comes to type-safe languages, that you just pick types and you ask the compiler to be the person that reminds, or the compiler that reminds you about things, and then you just move forward from there. And this is why you can get working software of a much better quality using effect systems, or using, at the very least, type-safe languages.
It reminds me of something I heard someone say, I don't remember who, but it said something like, every language has a type checker. The only difference is if it lives in the compiler or in the programmer's head.
That's a very good quote. I really like that. Yeah. And it's... But like Zio has much more than what we thought. You have structured concurrency. So you have the ability to spawn fibers, which is essentially grain threads. And like the parent that spawned the child fiber will be able to clean up resources, or like kill the child fibers when it needs to be killed, or like deallocated, or when its lifetime ends. It has the ability to model scopes, meaning that you can open a file and then using this scope mechanism, you can make sure that it's going to be closed, even if something unexpected happens. So resource management. And you have those building blocks for concurrency and for resource management that lets you build programs that you can control their behavior with, I wouldn't say configuration, but essentially what you declare. So it's a more declarative style of programming.
Yeah, and I heard there's a lot of like error handling primitives that you can use, like retries and all of these kind of interesting things.
And why you can use them is because you essentially create a blueprint of your program. So your effects, they just express a computation that hasn't happened yet in some data structure. And then you can just attach, or maybe attach is a better word to use here, mark those effects as something that needs to be repeated. And then the runtime will know to repeat them and to retry them if something happens with them. So we boil down again to some practical ways to create programs that are really convenient to use. It probably takes time to master, of course, but at least you have them and they tie together very well.
Yeah, we're running out of time, I'm afraid. I would really like to keep talking about Zio, but I just want to ask you one final question, and I think this is going to be like a standard question moving forward. Let's see what the audience says. But what do you think is the future of programming?
So for me, the future of programming is tied to type safety, languages that can express or can prevent you from stepping on landmines in production, for example. So prevent you from runtime errors, make illegal states unrepresentable, do work for you, because otherwise you have to do this work on yourself. You have to write unit tests for simple things that could be checked by a tool. And I think we should aim to have these kind of tools. This is automation in a way. So if you don't use Haskell or Scala and you say that, oh, I love automation, you don't love automation.
So reveal the preference.
You only love automation when you truly, even the tools that you use are automated or like works with some kind of they're power tools. So I think this is what will drive the progress in software development. I'm skeptical on AI in this type because it feels like it's supposed to be something that predicts text, not necessarily that has the abilities to do reasoning. But we'll see. Who knows?
Okay, but yes, thank you so much, Lachezar, for coming on the podcast. It's been a pleasure chatting with you about Zio and Scala, etc.
Yeah, thank you, Christopher. It's really great. Thanks for having me.
Yes, and you already mentioned your GitHub. Can people find you anywhere else? Like, are you on like Twitter or Blue Sky, or maybe you prefer to be anonymous?
In the words of a wise man, I'm on LinkedIn, unfortunately. But yeah, I kind of, I'm not super active in other platforms. I sometimes write on LinkedIn. But yeah, if you want, you can just follow me on LinkedIn.
Okay, yes, with those words, I think it's time to wrap up. But yes, thank you again, Lachezar, and
thank you.
See you later.
Yep.